Okay, here we go. So, ladies and gents, ready to go? Kim? All right, so we got Newton's first law. We're good with that. All right, we know that an object's going to move in the same direction it's moving in at constant speed unless there's another force acting on that, right? You saw that when you got the cart moving with the simulation, it was going, and as soon as you let go of the guy, right, the cart kept on moving at the same speed. Does that make sense? What did you have to do to get to slow down, Kim?
Put the same amount of force on the opposite side.
Right, you had to apply a force in the opposite direction. It doesn't have to be the same amount, it could be any amount. But it has to be a force going in the opposite direction, right? So that kind of tells you what Newton's first law is. The second law now. Second law is really, really powerful. Last week, about this time, NASA launched a space shuttle. It was a really important important test. Hopefully, in the future, it'll be a rocket and a space shuttle that'll send people to Mars. But the really cool thing about, Newton's about the space shuttle thing is that really all you need is Newton's second law to get the space shuttle into space, which is pretty awesome. Something very simple can send things out into space as long as you've got the technology to do it. So if we looked at Newton's second law and what you learned in your packet, right? I think it starts on probably page 2 or 3 of your packet to talk about Newton's second law. What did you see were the two things that affected the acceleration of the item? Not friction. So the amount of force, right? So we had force, right? And what else? What was the other thing that seemed to affect the acceleration of the box? The mass, right? So speed is a function of acceleration. So if we're accelerating, we're changing our speed. Right, so it's these two things that affect the acceleration of the object. Okay? What happened to the acceleration as we change the force? So if we increase the force, what happened to the acceleration, or the rate it changed its speed? It's sped up, right? So if we increase the force, the box or the refrigerator or whatever it may be, it got faster, right? It went faster? Okay, so we would say, if we're talking in math terms, we would call that directly proportional. Meaning if you increase one quantity, the other also increases. Okay? You heard that before, hopefully, in math? Right? What happened if I increase the mass? If you increase the mass of the object being pushed, what happened to the way it changed its speed? You know, Rachel? What happened? So if you increase the mass, right? So instead of like the box you use, the refrigerator, what happened to the acceleration? It decreased, right? So mass has an inversely proportional relationship. So that means if one quantity goes up, the other goes down. Okay? Make sense?
They're like opposites.
They're like opposites, right. So one force causes it to go faster, mass causes it to go slower. Think about when you're pushing a shopping cart. If you push with the same amount of force everywhere you go while you're at Market Basket, when the cart's empty, you can get that thing going really quick, fast, right? It'll travel. You can bomb around Market Basket, doing whatever you want, all right? But as you pick things up, right, and you put things in the shopping cart, you increase the mass of the cart. If you push with the same amount of force, the cart goes more slowly, right? It's slower. It's really hard to get it going. You got to give it a good push to make it move. Okay? So these are the two things that affect how how the object accelerates. All right? The way that we can show their relationship, that if they're proportional to each other, right? We say that they are up here, right? So if we're talking about an equation, acceleration equals force, so that means if I want a greater acceleration, the force also needs to go up. But if it's inverse, meaning if one goes up, the other goes down, I need to have that in a denominator. Right, so we have to have that over mass. Right, so this is basically saying that the acceleration is equal to the force divided by the mass. All right? This force is the net force. Right, so it's the sum of all the forces. And you saw that in the friction, right? You saw that in the friction part of it. If where you pushed on the block with a 50 or 100 newtons, the box didn't go anywhere because friction canceled it out on the other side. But once you got to 150, they gave you that little sum of forces arrow on top that was not equal to 0, and that caused the box to slide a little bit. It caused it to move. Okay? So we can rewrite this to make it a little easier, right? Acceleration equals force divided by mass. Typically, you would write instead, you would say F equals ma. Force equals mass times acceleration. Now this F is F net. Again, the net force, the sum of the forces. So you would add them up. In whichever direction that net force, or the sum of the forces was going, that's the direction it would accelerate. Okay? You may see it as F net. You may also see it sometime as sigma F equals ma. Okay? F net, right? The net force is the sum of the forces. This is the Greek letter sigma, which stands for sum. So the sum of the forces. These two are the same thing. Sometimes you'll see it like this. Sometimes you'll see it like this instead. Okay? But I think you saw, and they even gave you in the packet, they told you that, right? Acceleration is proportional to the force and inversely proportional to the mass. Right? And you saw that in your simulation. Okay? It makes sense? Right? And that's really Newton's second law. We take this relatively simple equation and we put it together with those free body diagrams, life gets really easy. Okay? Or the two of them, you get two simple things that are really, really powerful, and you can solve all kinds of things with it. Okay? Any questions? We're good? All right.